Okay. Okay. Well, thank you for accepting the invitation, Joanna. So you can start when you want.
Okay. Thanks so much for the invitation. It's really a pleasure being here at your seminar, even physically being here in the city. Yeah, so I'm going to report a little bit about a project running joint with Pablo on computations of highest weight vectors in tensor products for the Lie algebra SLNC. So I already fixed a little bit of notation. I hope that's fine for those taking notes. Yeah, we're considering the Lie algebra SLNC as n matrices. All coefficients are all the time over C with trace equal to 0 and the usual matrix commutator. And we fix its usual decomposition into upper triangular, diagonal, and lower triangular matrices, from which we also take the typical generators Fi, Hi, and Vi. And I also want to remind of taking the universal developing algebra of that Lie algebra and being able to rewrite it using the PDW theorem into also some triangular decomposition into these three parts. So so for this Lie algebra or for this algebra, we will consider only finite dimensional modules in this talk. So let me also briefly remind you again a little bit of what's going on for the finite dimensional modules. Yeah, maybe, I don't know, so one can see the whole whiteboard, right? So finite dimensional modules are, first of all, completely reducible into sums of irreducible modules, which makes it even more important to understand the classification. So I also briefly reminded you of this one. Of the irreducible representations. Everything finite dimensional here. So they will all look like highest weight modules and lambda. So where these are modules where it's particularly important to know that there's a vector that has the property that it is annihilated by all the EIs, and Hi acts by a scalar given by some lambda that's labeling the module. Where lambda is not only in the dual of the cartons of algebra H, but in order to give a finite dimensional irreducible one, it needs to be the dominant integral weight. Which can be, either you already know the theory, or let me just give you like very explicitly what it is. So in particular, in here we have some elements that will just pick the ith diagonal entry of the diagonal matrix. Think of everything being really very completely realized. So pick ith diagonal entry. And then this subset here is given by the span over positive or zero integers over some epsilon 1 plus the second fundamental weight and so on until epsilon 1 plus epsilon 1 and so on. Every such highest weight belonging to finite dimensional reducible module needs to be of that form. So it's just like a z greater equal 0 linear combination of these weights. And so if we write lambda in terms of these epsilon I and we collect the coefficients, then we find that lambda 1 has to be greater equal than lambda 2 and so on, greater equal than lambda n, which gives rise to these famous Young diagram pictures that encode such a weight with the first row having length lambda 1 and so on until the last row having length lambda n. So it's a very ugly one.
Still okay.
Old staircase. Old theories, so staircase got a bit rotten. Okay. Yes. I mean, if there's any questions, also feel free to interrupt me. Or I'm also happy to, I don't know, after the talk, discuss more about the background. But I think just combinatorially, you can just use what's currently on the whiteboard. And now, tensor products now. Since the universal enveloping algebra is a algebra with co-products, so we can have some new action on a tensor product of two such modules that's induced from the old actions that we had already. So in particular, what's interesting for us is when we take any guy from up here and we tensor it with this epsilon 1, then we get, like here we see some of modules. It decomposes again by this complete reducibility. So we can ask, like, how does it decompose? And well, it will display all the weights of that form, running in principle over all epsilon 1 up to epsilon n, but only such that we get again a dominant integral weight. Now, to just demystify this a little bit, this representation here can be realized as just the natural representation, the n-dimensional C vector space with SLNC doing what it can do best, which is acting as matrices and vectors. So that's the natural representation. Why is it written in this funny way? Well, and there's a highest weight vector v epsilon 1, which is in this realization nothing but like kind of the first standard basis vector. And indeed, so when we act with kind of upper triangular matrices, then no one sees this one up here, and so everybody maps that guy to 0. So indeed, it's the highest weight vector. Maybe let me also say that the weight decomposition. So just as a vector space, this thing here decomposes into one-dimensional weight spaces that are labeled by the epsilon k, which are just given by the k standard basis vectors and their spans. So and from this one-dimensionality of these weight spaces, there comes this important property that in this tensor product we will only have at most one copy of each irreducible, which is therefore uniquely determined. So typically when looking at bigger tensor products, this might not be the case. So we might not be able to really pin down exactly where the summands are, but only the isotypical components. But here this is possible, so this is multiplicity free.
Can I sidetrack for a bit? I mean, it's maybe going in a completely different direction, but there is all this work by Hernandez and Leclerc about cluster algebras based on this. They have is something similar to this, or not necessarily? I think they see some cluster algebra structure appearing in.
Yes, I don't have this. I'm very happy to look at this after the talk. So I mean, this would be just.
Right.
I just need the very classical.
Okay.
Like we're really without any kind of upgrades. And this is also. I mean, we are talking about like I guess something around the range of 100 or year-old theory. So that's why the staircase is going. And now the thing is, actually, like that's a very good moment to pause for a moment. This is like this really old theory, but now the question is, even in this multiplicity-free case, we can, I mean, this decomposition here is kind of just an abstract decomposition, right? So we know that there are summands that are just isomorphic to our abstractly constructed highest weight modules, maybe as the usual like simple quotients of Vermers or something like that. But here we have an honest tensor product, and its its elements look like linear combinations of little tensor products, right? So the question that we were wondering about in our project, the first question would be, to squeeze it here, but would be like how do the highest weight vectors, which I will typically abbreviate like this, how do the highest weight vectors in this tensor product really look like? And then we will also look into the tensor powers of the natural representation. Mainly for two reasons. First of all, it's again somehow strikingly simple as a question, right? I mean, that's tensor powers of just a natural representation, which is one of the easiest representations of the algebra you can possibly think of. And it has the really nice really nice fact about these tensor powers is that sooner or later, so if you look at high enough tensor powers, then every simple will appear somehow in these tensor powers. So kind of like all tensor products of finite dimensional simple modules take place in kind of that ambient vector space, if you wish. So one can kind of study this there concretely.
Is this a general fact? I mean, is it a null result or something that you need to prove?
No, this can be seen somehow quite quickly. So when one reiterates like these tensor products, then so when we have let me phrase it in Young library terms. So as soon as we are in a large enough tensor power so that we have as many boxes as lambda needs, so d boxes to fill up a lambda, we can find
Right.
a lambda in the tensor powers. So actually people did so I don't know, so there's this theory about crystals. Instead of actually looking like into these tensor powers as modules with living vectors inside there and so on, what people would usually do would be to actually try to avoid this and just purely study the combinatorics that arise by doing all kinds of like very nice, also quite old constructions. And there's another motivation to actually like look at these tensor powers also somehow for us would be that that's like kind of the prime example for probability with the action of SIN, as I just described, and commuting and centralizing SD action of the symmetric group that will commute the tensor vectors. Where there's also like it's really nice to see somehow the combinatorics of how these modules decompose.
Right.
Like there's all kind of beautiful pictures for that, but somehow to go like just one level below, saying how do actually the highest weight vectors in there look like when we have so plenty, like it's such a beautiful and rich theory to describe these tensor powers. Yeah, can we actually go back and see really what the highest weight vectors look like? So let me start looking into that. So some observations. So immediately, and also always independent of the lambda, we have that L lambda plus epsilon 1 is appearing in that tensor product. There the highest weight vector, which is here maybe just abstract, can be realized very easily as just the tensor product of the two highest weight vectors here. Yeah, remember, like this is still just the first and the basis vector, and that would be like the given highest weight vector that we have here, and somehow since highest weight vector, tensor highest weight vector is always again some highest weight vector of the added weights. This guy is always there and always easy to find. Okay, maybe let me do a little example to illustrate that there can be kind of gaps in the epsilons that give rise to new summands, just to illustrate a bit what's going on there. So let's say let's take n big enough, whatever. Something like 10 or so to have some bigger example. And let's just start adding weights so that it's lambda 1 is greater or equal than lambda 2, greater or equal, now equal to lambda 3. Let's do another epsilon 4 or something like that. So when we look at such a guy, then we will find, well, the guy where we just added that epsilon 1 So that will be there. Now we ask whether we can add epsilon too, and that's also fine because that these inequalities for the lambda I will still hold. So that would be for epsilon 2, epsilon 3, plus our epsilon 4. Now we are asking for epsilon 3. Can we also do that? And then we see, oh no, this actually doesn't work because then we would have that our new coefficient for the epsilon 3 would be 4, so which is not greater or equal than 3, right? No, vice versa. So 3 is not greater or equal to 4.
Yeah.
So right. So there's like one that doesn't work. Yeah. So but well, I mean, happily we could continue. So there's epsilon 2. I shouldn't have made an example with 3s and epsilons. That's like the oh, we can add epsilon 4 again because there again 3 is greater or equal than 2. And then we can also add some epsilon 5 in the end. But then for epsilon 6, 7, 8, whatever, until we reach our 10, this doesn't work anymore because we are otherwise we would have like some kind of lambda.
Yeah.
9.
1 is bigger than 0.
One is bigger than 0. Then well, sorry, 0 is not bigger than 1. So that's the issue there. Yeah. So this stops, but we also have like a gap in between. Yeah. So these kind of things can happen. But this guy is always there. So that's like a very reliable. And now I was promising you like, oh, now we need to look at how are they actually realized. And the first example I'm showing to you is already there. Yeah? I mean, this is already realized as an element in here very explicitly. Well, okay, that was easy. So we hope for the best and go on. Yeah, and then so as soon as you start like looking for the kind of higher epsilon case, it starts up kind of getting just annoying. So when you just like take a piece of paper and try out, like I mean, it needs to be highest weight again. Yeah, so to get some highest weight vector, we know that epsilon I times highest weight vector must be 0 for all I in particular. Yeah, so this gives n-1 equations to be solved. There might occur quite a lot of summands actually, because so if we have something living in the tensor product, then we need to apply the co-product to EI to see what it does. So that's EI tensor 1 plus 1 tensor EI. Yeah, so when we just apply EI, we double up the summands that we already had, and so it gets a bit bulky. Yeah? So but let's just like be brave, yeah, and try to observe what's happening. So so if we know that there's some d lambda plus epsilon k for these combinatorial reasons, yeah, it must be there in lambda there's epsilon 1 for plus epsilon k. 1 integral. But it also needs to have weight lambda plus epsilon k. Yeah? So we need to look inside this weight space here for this vector. It must be in there. And so since it has to be of the form, we just look at how does this weight space look like. Yeah. And so we find that, well, we can't really know how this lambda looks like that easily, but we know very easily how our natural representation looks like. Yeah, remember it has the weight basis given just by the standard basis vectors. Yeah? So we're not talking anything complicated here. So it is of the form like just something in here. For some wi's, and now since these weights need to add up to this lambda plus epsilon k, we know that this infinite L lambda has to be in the weight space lambda plus epsilon k minus that epsilon I that we are currently looking at. Yeah.
Yeah.
Yeah, so let's check this. So here we just chose any weight vector in a lambda, so that that vector being of weight lambda, well, plus epsilon 1 minus epsilon plus epsilon k minus epsilon 1, plus that epsilon 1 here indeed has weight lambda plus epsilon k. Okay, and this is also true. Let's check here. Wn. This should have weight lambda plus epsilon k minus epsilon n. But the whole guy here has weight that plus epsilon n, which is equal to lambda plus epsilon k. Yeah? So it must be of that form. Now by looking at these equations for all I, we find our first little lemma, which comes out very innocent. So, what have I just written? By evaluating these equations that characterize the highest weight vector, we will find that actually these W's are not just some basically random elements in the correct weight spaces inside a lambda, but they actually all depend on one another, and last but not least, all on the W1, because when we inspect these equations, we find that Wj plus 1 needs to be equal to minus Ej applied to Wj. Yeah, so let's just verify this. So we have that 0 is Ej applied to our v lambda plus epsilon k, which we chose to be of that form. So by this whole product, let's first always apply Ej in the first tensor factor and then always in the second tensor factor. So that would be Ej W1, the epsilon 1, plus Ej W2, the epsilon 2, and so on. This Ej n epsilon n. Plus, now always in the second factor, but here you will see something happening, which is that which is that EJ given by this J of diagonal elementary matrix, that will actually act by 0 on most of these guys, except on now index war. So EJ on V epsilon I is 0 unless that I was just the J plus 1. And then it will send it from V epsilon J plus 1 to V epsilon J. Yeah, that's what the EJ does. And it's 0 on all the others. So in fact, we're looking at quite a lot of zeros. But keep in mind that all the V epsilon I are linearly independent. So are somehow all of these summands upstairs. Yeah, we find that by just comparing, so what was the only place where EJ, the epsilon I was something non-zero, that was for that, yeah, the epsilon J plus 1.
Mm-hmm.
Yeah, and so we get that the epsilon J has to be equal to that double so EJ WJ and the V epsilon J must be equal to so we had this WJ plus 1 and epsilon J that's somehow resulting in the second line. Yeah? So that's coming from the second line, that's coming from the first line, but since the sum needs to be 0, these guys must be the same. So EJ WJ must be the same as minus WJ plus 1. And up to the sign, this is what's standing up here. Yeah. And even more so we also see that for any other index, we see that EJ WI is 0 for all J not equal to I. Right?
Mm-hmm.
So, and this in particular holds true also for W1. Yeah. So W1 is the only guy we don't know anything so far, yeah, because we just know that all the other higher W's are basically all stemming from the W1. But the W1 has also some characterization, which is that yeah, EI W1 is 0 for all I between 2 and n-1. Yeah. And that is pretty strange actually, because this means that W1 is annihilated by some lower corner SLN-1 sitting inside SLN like vacancy somehow full. Yeah? So that thing here will annihilate our W1. Yeah, and yeah, so we suddenly find like this kind of lower corner SLN-1 to play an important role, yeah, for the weight vectors that can occur as summands for our one and only up to scalars highest weight vector that we want to construct. So let's elaborate on this a tiny little bit more.
Why W1 is animated by F shapes? EIs are upper or lower triangular matrices.
The EI would be upper.
And why is animated by some lower triangular matrices?
I mean, just that the coefficients will be somehow too far away from that one that we have. So, sorry. So we have sorry. Yeah. Let me not say it like that. Sorry, I shouldn't have said it like this. I mean, like that. Yeah, like that. Corral somehow in here, right? I mean, that just what's meant by the ease. So, but it's just that this SLN-1 is somehow playing like kind of a role of like this W1 will be a highest weight vector with respect to this SLN-1. Oh, okay. Sorry, yeah. No, it's annihilated by all the e's, yeah. But it's but this means that it is somehow killed. Yeah, and therefore like a highest weight vector for this lower corner guy. Thanks for clarifying. Yeah, let me I mean, so now we were kind of just assuming that we had already some highest weight vector and looking at, okay, what do we learn about the shape of it? Yeah? But now let's be brave and just try to do it vice versa. And say that we just take some non-zero W in that correct weight space. So that would be lambda plus epsilon k minus epsilon 1. Yeah. Because we want it to be like the W1. So it needs to be in that weight space. With exactly that property, so that all the e's annihilate for E2 up to En-1. And then we indeed find that this such a vector produces also a non-zero highest weight vector in a lambda tensor L epsilon 1 through that formula that we have somehow just concluded in the other lemma, which would be the alternating sum until we reach plus minus En minus 1 to 1 n. Yeah. So in other words, it's really like there's a very close connection between yeah, such W annihilated by this kind of yeah, smaller yeah, E2 up to En-1 and a resulting highest weight vector in the tensor product. Yeah, they always come together. So kind of already when without having even tensored anything yet, if we just somehow find such a thing, then we know that it will give rise to a non-zero highest weight vector in here, yeah? Through that very formula that we have just constructed just from the observation of what actually happens when we evaluate our equations. Yeah, all e's need to annihilate a highest weight vector. So we find that this characterizes that. So let's maybe put this as a little remark. So number 1 and 2 together characterize somehow this the highest weight vector b lambda plus epsilon k by this kind of almost highest weight vector, so this kind of lower corner highest weight vector. W lambda plus epsilon k minus epsilon 1. So in other words, we can kind of predict how this vector looks like if we just looked at lambda. In this kind of lower corner highest weight vector, this is actually not only like kind of a nice observation, that it has the shape, but this is actually really instructs how to compute it. So it gives a computational approach for finding the lambda plus epsilon k through W lambda plus epsilon k minus epsilon 9. And this would be what I would turn out to. So actually like this.
Can I ask something? The condition lower corner highest weight vector on this lambda does not imply that it's a weight vector for.
It is, so sorry, it is a weight vector for everything. So it's lower corner highest, somehow full weight vector.
So it
is here, it's really a weight vector.
Yeah, okay.
Here it's a full, so maybe let me.
It's a lower corner higher weight vector for the other thing, but
vector.
also it's a weight vector
For the whole thing. Yes.
But I mean it's
Let me put it like this, like lower corner highest, but weight vector for the whole thing.
Yeah. Okay.
Yes.
But you need to ask this extra.
I can't just forget about the action of H1.
Okay. Yeah.
Indeed. Yeah. And, I mean this still needs to be like in the correct weight space. So let's try to find W. Yeah. Okay. Find W. Okay. So here we don't have to look at all these different weight spaces anymore, but only at one, right? I mean, just this one weight space is our hunting ground for the W. So let's first describe whether we can kind of understand how the elements in here look like. Yeah? And actually, so just for the weight reasons, this is given by all monomials in the universal enveloping algebra and whatever they span that have like the correct weight epsilon k minus epsilon 1, yeah? So that when I multiply this with the highest weight, yeah, I go down to that weight space where I want to end up. So let's try to understand what monomials in F we find here in order to understand linear kind combinations of what we have to study to find our W. Yeah? So
what is that's an equality?
yeah, like so applying all of that UN minus epsilon k minus epsilon 1 to the highest weight vector and all linear combinations thereof, all scalar multiples that will give that weight space. So this is like actually this will just be subjective onto this as the vector spaces now, because so think of this is kind of just looking at this one weight space in this Werner module construction of well maybe I don't know if I'm now using notation that's bit off, but so here that would be like kind of the one-dimensional space on which h acts through lambda and plus x by 0, and then so since we have this DBW theorem just as a vector space, this will be just like n minus, the only thing surviving because we can pull everything else to that somehow linear vector up here. And so then we just need to look at, so here's like these linear combinations of monomials in the Fs. Yeah? And so if we just look at this weight space, then this will all come somehow from that corresponding weight because they will add up for getting back weight gets. So if we are somehow very generous, let's just look at kind of any monomials and we don't have a linear independence at first. Yeah. So what monomials in here will have just the correct weight? So as long as we keep multiplying FIs, so k minus 1, many of them, so that k minus 1, and each index occurs precisely once. Then we will find that, so each of them, so the first one will be like epsilon 2 minus epsilon 1, then the next one will be epsilon 3 minus epsilon 2, so we get like a telescope sum of the weights leading up to this epsilon 3 minus epsilon 1. And for this weight consideration, doesn't matter in which order they occur. We just need to make sure that we hit each guy once, so that the telescope sum works nicely and we end up in that phase. And now notice that I and fj commute if the indices I and j are far apart. Yeah? So actually we will have done quite a lot of overcounting if we just look at these. Yeah? So maybe we can do it better. So want to be more efficient. So let's try to order the monomials at least a little bit to get rid of too many extra counts that are just due to some very stupid commutation relations. Yeah, so for this, we consider some sequences theta of k minus 2 arrows, either pointing up or down. So, for example, we could look at something like that. Yeah. So, and this will encode ascending and descending little sequences of fi and fi plus 1 and fi and fi minus 1 as follows. So I don't want to give the formal definition for this talk because that's like just a very big index mess. But like here we would have k equal to 5. And let's just look at what would be somehow the f associated with such a thing. So we always start at f1, right? I mean, f1 needs to appear. And then the first arrow indicates that now we are kind of increasing the order. So here comes f2. The second arrow says how f3 occurs now. So again, increasingly f3. And now f4 needs to be in a decreasing order. So we just put it to the very front. Yeah. So that would be f of that theta underlined. Yeah. And observe that, I mean, we could have written this f4 also by commuting it past f1 or f2 somewhere else. Yeah, but let's just do it like that. So this theta I kind of encodes whether we have fi plus 1, this is for theta I an up arrow, or if we have fi plus 1 coming before fi, that would be for theta I.
So you start with f1. If you have an up arrow, you put something to the right, and if you have a down arrow, you put something.
Yeah, exactly. And if I let's just say we have k equal to 6, and we put another up arrow here, and then f5 would have to go on that side again. So they don't have to, like meet immediately, because there can always be some j's in between that just have some index far away from I and I plus 1.
Yeah.
So this what happens here.
Yeah, because commute.
Yeah, exactly. So the only somehow f guy that's interesting for this f5 in here would be the f4, right? And as long as we are to the right of that one, it's the same monomial, right? Yeah. So that's just like a more efficient way to encode this. And it turns out that this is also very convenient for computations, this notation. Let me.
And this gets rid of all the ambiguity. I mean, because you were
not necessarily. So I don't even care. It's okay if I still have some ambiguities left. Actually, like that would be, so these f thetas would be a basis for this.
Mm-hmm.
But now, I mean, we are honestly interested in that space. Yeah. So where there will be again some flashing as soon as we apply it to the lambda. Mm-hmm. But we don't care. So we get a spanning set that is more efficient, though not fully efficient. So that lambda in that weight space is actually spanned by f thetas applied to the lambda, and these thetas are up-down sequences of length k minus 2. Yeah. So if we assume the convention that we always start with f1, yeah, then just saying how long the sequence is will already encode what weight we get out. Yeah? So but no, that there might be even some zeros in here now or whatever. I mean, we don't even care about this so much. We just want to know that we have a spanning set that is easy to manipulate for computations. But notice that we need to be very careful about something being non-zero, something like that, because we can't argue with linear independence within that set. Yeah, so it's just a spanning set, but good enough for us. So I need a bit more space, so I'll put it here. So keep in mind that we want to solve for epsilon I ei w lambda plus epsilon k minus epsilon 1 equal to 0 for between 2 and n minus 1. So maybe we look at what ei does to each of our generating guys and to have some tools at hand. Yeah? So maybe one thing to note already, something that will very commonly happen is the following. So when we apply ei to something that's maybe let's just look at fi v lambda. Yeah, it's a little toy example at first to show you the flavor of the computations. Then we can actually add a 0 because v lambda is a Higgs weight vector. So we can write ei fi minus fi ei v lambda, because this ei will hit the v lambda first. That will be 0. Yeah, so we have a free summand. So that would be actually hi v lambda. So which is just then that multiple of v lambda. Yeah. So that is something that we will very commonly use. And just imagine there was now some funny looking fj around with an index far away. Yeah. Then we could first somehow compute this away. Yeah. And out. So we will just find something like of that form. Yeah. Yeah, j, let's say I plus 5 or whatever. Yeah, so they're far away. We can just do something like that. Yeah, so that was really just meant as a little example. I will already erase it because I need some space, but just to give you some feeling of what will happen now in the background of the following lemma. They are all called lemmas, by the way, because they are all somehow so easy, but the observations still keep failing. So I apply to one of our generators and theta times the lambda is actually of the form. We keep somehow the first I minus 2 bits of the sequence, yeah, because that will be the part where ei just walks past without noticing. And then there will be also in some kind of leftover parts for theta I plus 1 up to theta a minus 2, like for the remainder of that sequence. And there we need now to do some index shift, so we don't start at f1 again, clearly, but we start at I, yeah, so let me denote it like that. So that would be index shift by I. And then we kind of bump out hi as before, but there might be some coefficient as well. Unlike in our little example. Where this C, depending on the arrows somehow coming before and after that fi of interest for this EI. That will be either 0, 1, or 2. And it will be 0 if theta I minus 1, theta I was up down. It will be 1 if this was either up up or down down. It will be 2 for the case down up. Yeah, so very quick sanity check. Yeah? So what would such a bit of the sequence encode? So that would mean that so we would have an fi minus 1 somehow as the last thing that we had. Then the theta I minus 1 would encode that there would be like an up afterwards. So if I comes afterwards. Yeah, but then there's a down. So if I plus 1 comes before that whole thing. Yeah? So if EI happily comes like attacking, then it will just walk past these two things and just hit the FI. Yeah? So it will create the HI kind of immediately and can walk safely past all these FJ that are like far apart in the index. Yeah? So and vice versa, like the other case here, yeah, that would be that we start with the down arrow. So actually we have fi minus 1 coming only after fi, and then we have the up arrow, which is fi plus 1 comes after that as well. So ei hits the fi, but then the hi created at this moment by the highest weight vector working around in the end of the monomial, that hi has to walk past fi minus 1 and fi plus 1, yeah? Collecting plus 1 in each set, giving rise to that 2. Yeah, that was basically already the proof, but it's really just a small computation. And now we were kind of with this with these two arrows, we were looking at ei kind of in the middle of the sequence. So that was the C, and we had I was less or equal than k minus 2. And if we had k minus 1, yeah, which also needs to act like 0, then this will walk past most of that sequence. And so our h k minus 1 minus some coefficient depending just on the last arrow is either 1 or 0. So yeah. Again, like is 0 if the last one was enough. Sorry, is if the last one was a down, and is 1 if the last one. 0 if k minus 2 was enough, and 1 if k minus 2 was down. Okay. Yeah, so we have already seen this somehow here in this little example. Let me maybe do one more example, because this might look unsatisfyingly combinatorial, but it's actually really easy. So when we look at our little example that we had before, so we had this F4, F1, F2, F3, F5 thing. And when we want to hit it with, say, E2, then the E2 doesn't care at all somehow, so it doesn't even quite see like this part or that part. It only cares for this bit. And so here this was where we had an up arrow and another up arrow. Yeah? And indeed, so it walks past this F1, so this it kind of also ignores, then it creates the H, then so it is like F4, F1, H2, F3, F5, and when we combine these two guys, we collect this plus 1, so we have F4, F1, F3, F5, H2 plus 1. And again, I have to put a d lambda because otherwise then we wouldn't get an H2 from the commutation. And now this, here this is like nice to see that they come not immediately as organized as here, but here we have like just the F1, and then we have F4, F3, F5, H2 plus 1, which are the portions belonging to, this is like F of the empty set, no arrow at all. And this is the kind of remaining chunk of this thing, which is a down arrow and an up arrow for the index 3. Right. And this is our C up arrow, up arrow. Right. So I hope this demystifies a little bit the notation. And it also explains why these up-down arrows are kind of really nice. And one word of warning, if you're kind of used to that kind of theory, then usually with up and down things, you might associate rather applications of E's and F's. But here we are just in the F world and we're just comparing DBCs, just as a word of warning. And then with this lemma, it's actually so keep the task because this is exactly the headline we need now. So just by brute forcing our way forward, let's see what we get. So we define for such a sequence theta in down arrow sequences of length k minus 2 polynomial. That we call p theta underlined, and it's actually a polynomial in the variables h2 up to hk minus 1 that we obtain as a product of smaller polynomials which depend, so for each I, on one of the theta i's, I equal 1 up to minus 2, and that have variables in hi plus 1 up to hk minus 1. So it's a polynomial living in the universal enveloping algebra of the Cartan. So since this is commutative, like this is an honest polynomial up here. And now these need to be explained. And so these polynomials are either given by hk minus 1 plus hk minus 2 and so on up to hi plus 1 plus some linear term k minus I plus 1 if the theta I was an up arrow and is given by minus the whole thing. Minus k plus I plus 2. So it's like a different condition if we are having a down arrow. So so depending on, so we can read off our sequence, and depending on whether we have an up arrow or down arrow, we have that other term that we multiply get some bigger polynomial.
Sorry, Joanna.
Yeah.
In the first formula, it's a minus 1, not a plus 1.
Yeah. And then it's also and it's a plus 2 here because we inverted that sign. And yes. Thanks. Sorry. So these polynomials are made in such a way so that now we're very close. We set lambda, w lambda plus epsilon k minus epsilon 1 equal to the sum over all such up-down sequences of length k minus 2, where we have that f monomial, and as the coefficient, we have this polynomial in the h's, which, since we apply it to the lambda, will be actually a coefficient in z or c, right? I mean, this will be just a linear coefficient. And so, indeed, we are now looking at the right weight space, and so the statement now is that indeed, with this choice, z1 is 0. Oh, I flipped from ER from 2 up to n minus 1. Yeah. So, and maybe let me just mention two things about the proof. So first of all, for indices that are way larger than this, yeah.
Sorry. This polynomial I to be lambda, that's a multiple of the lambda.
Sorry?
P theta.
Yeah.
That's a number.
That's a number. Yeah.
Oh, okay.
Because it's a polynomial in the h's and the lambda is a weight vector.
Okay.
So it will be just replacing each. I mean, that will be just very somehow applied to the lambda is just p theta, and then like plug in the lambda, like evaluate the whole thing at lambda, or think of it vice versa, evaluate lambda at p theta, whatever you prefer. So this is yeah, exactly. And then the f theta moves it somehow down to that weight space where it should go. And so whenever we have, now let me look again because of its indices. So if r is greater or equal than k, yeah, then this is somehow okay just for weight reasons. Or you can think of, I mean, that er with greater or equal to k will just happily walk past all these f's and kill the f lambda itself right away. Yeah, so this is already okay. But for r lesser or equal than k minus 1, one needs to do something about it, because there it really starts hitting these things. And you see, whenever EI meets a single of our f thetas, it will start causing yeah, these terms with hi plus c. So and so it will, would kind of look messy, but actually these p's were made in such a way so that they precisely compensate for that. And so this is also okay by recursion satisfied by these yeah, PIs. So I will write it down just to give you an idea why kind of the recursion matches precisely with what we get in the computation. So first of all, so the recursion starts at the biggest index at k minus 2. So there, for an up arrow hk minus 1, we have directly by this definition hk minus 1 plus C down arrow. Yeah, so if we unravel what this integer is, this will be just the C down arrow. And similarly for pk minus 2 down arrow of hk minus 1, here we will find that this is minus hk minus 1 plus C up arrow. Yeah, so already at this start of the recursion, you will see that, so we throw in signs so that somehow up arrows will, yeah, so like the coefficients for a down arrow will be precisely minus whatever we get for an up arrow. Yeah, so this will give rise to some cancellations. And similarly for somehow the rest of the recursion, so whenever we have pi minus 1 of an up arrow of hi plus 1 that's up to hk minus 1. Then this is actually computed from the pi up arrow in hi plus 1 to hk minus 1 times hi plus C down up plus pi down arrow hi plus 1 up to hk minus 1 times hi plus C down arrow. And let me put pi minus 1 down arrow here, because this is, so I'm not writing now the h's it depends on, it's just like for the sky. So this will be minus pi up arrow times hi plus C up arrow down arrow minus pi down arrow hi plus C up arrow. Yeah. So this is not the argument, this is the product.
Right.
Yeah. So right, I mean, since these p's satisfy such a recursion that is made so that there can be good cancellations when we hit our W with the ER, yeah, we can really kind of just reinforce this thing to satisfy these equations. Yeah, so that's the upshot. Yeah, now that we have this this W, it's then just the corollary from like the lemma that we had already in the beginning. Like this W indeed produces some highest weight vector, and indeed, let me just write it like that. So if this W lambda plus epsilon k minus epsilon is not zero, yeah, which is totally not clear from writing it like this, yeah, then again, like the sum over and the other alternating sum that we have seen earlier together. I might be changing actually the signs, but I guess like an overall sign for the highest weight vector you can bear with E1 applied to F theta. So this is like the highest weight vector. Is now is epsilon 1. So as explicit as we wanted it to be, because we wanted to write it as a tensor product, we did it in here. Yeah. Highest weight vector for the copy of lambda plus epsilon K, that's also, yeah. So since this is unique up to scalars, the size weight vector in here, we also know that we couldn't do any better, kind of. Yeah, I mean, we can compute this also and try to simplify, like these expressions, but this is up to scalars the highest weight vector inside here. So that is somehow what we wanted to get, and let's just maybe as a very little example remark that if we look at k equal to 1, yeah, that was the example at the very beginning that we started with. That was the only easy case. Then indeed, this boundary formula simplifies to become just v lambda tensor the epsilon 1, so that's good. And for k equal to 2, then our w lambda, so here w lambda plus epsilon 1 minus epsilon 1 is just equal to lambda. Yeah? So but here the w lambda plus epsilon 2 minus epsilon 1, that's actually, I mean, still here, the only theta sequence that we have is the empty set. Yeah? But for the empty set, we have one monomial, which is just f1. Yeah? So this is just f1 applied to lambda. Now this alternating sum will give that v lambda plus epsilon 2 minus epsilon 1 is equal to. So first we just take that guy without changes, and then it's minus e1 f1 e lambda and then the epsilon 1. Yeah, so this e1 is coming from here. And probably I want to have something like that. So that side. Yeah. So so here this is here one can already see certain room for simplification, because again e1 f1 applied to v lambda is the same as h1 applied to v lambda. Yeah? And actually this was also turning the whole talk around now. This was actually something computed by hand before the whole thing started, but and then even like for k3, where this thing gets already like impressively many summands, this gets nasty really quite fast. So but I mean, one can still do it by hand to solve that, but I think yeah, with this pattern that's actually working in the background with these repeaters and so on, that are much more satisfactory than just having the plain formula. But if you, I don't know, I guess I'm already like yeah, exactly like having 3 minutes or something like that.
Oh, it's okay.
Yeah. Because then as the dessert, I would look into tensor powers and say what's somehow problematic about them, but also say for n equal to 2, what one can see, kind of using exactly this example.
Have you implemented your formula already?
Yeah, so actually, funny enough, we do have an implementation, but this is not just implementing this way around, but the hardcore other way around,
Okay.
which is for these tensor powers. When we think of the Cheval relative story in the background, and I think so Pablo already gave a talk about this something like 2 years ago, about how actually there's this notion of a Drusius-Murphy projector, which is a projector that will actually pick out the highest weight vector from a tensor power. So that's an operator, and yeah, they're like really using this theory of these Drusius-Murphy projectors. We have some stage code that will actually do for some arbitrary n and d. Yeah, you give me like a path in branching for yeah, n and d, and I can give you a highest weight vector if I ask my laptop and let it get really hot and really
Work for a bit.
Actually, the implementation is not very efficient. Yeah, but
Right.
and that's actually very, very helpful as some kind of example material. So I mean, the things that I'm presenting now are kind of still rather independent of this example material, because that was like for, precisely for going beyond this here.
Right.
But yeah, even for these kind of, I mean, to just know what one is searching for, exactly, that is very helpful. So this here, so the formula for lambda plus epsilon k inside R lambda epsilon 1. And this allows a recursion in theory. So in theory, allows a recursive description. That's it. Description of the highest weight vectors in tensor powers that are obtained from branching. Yeah? So in here, this is not multiplicity free anymore. So here in this big tensor product, we will find like many copies of the same simple module. So a priori, there's no natural choice of one copy or another, which breaks down to the highest weight vectors. There's no like overall natural choice anymore of the highest weight vectors. There it would be just either in terms of describing the span of like all the highest weight vectors for that isotypical component, or it would be if you also prescribe that I want my highest weight vectors to come from branching, then you make them unique up to scalars again. So in these unique up to scalars highest weight vectors that come from branching, they could in theory be described by a recursion describing these guys, because so what's happening is that when we take this tensor power and consider it as taking first only d-1 tensor power and then tensoring with another copy of the natural representation, and then assuming that by this recursion from the branching we have already decomposed this guy, then for each of the summands in here it will be just another application of our formula to derive the next stage. Yeah? So this will create more and more generations. Unfortunately for n greater or equal to 3, this is like really hard just because these formulas are bulky. Yeah, but for n equal to 2, one can do something about it. I will switch vectors for branching in. This is not really overkill notation for tensor powers of the two-dimensional representation from branching. So for just is it 2. Yeah. When following kind of this recipe that I just described mainly in words down here, then we want to compute highest weight vector that we want to denote by Vt. So when T will be a standard Young tableau, highest weight vector Vt somehow sitting inside. Let me also write LT for that simple module, which is the summand inside the isotypical component of lambda inside. As you can see. Depends on power. So, but we want to describe this for standard Young Tableau T shape lambda. We want to describe it really not as an abstract element again, but really as a concrete element living inside here. So how does a concrete element living inside here look like? Well, it's a sum of tensor monomials of length d. Yeah? So it has coefficients that will kind of depend on the monomial and on that t. I'm introducing another notation, which is yet another tableau that encodes actually the tensor monomial. So where J is not a standard Young tableau, but it is a row strict filling of shape lambda that encodes the tensor monomial the epsilon I1 tensor the epsilon I2 tensor blah 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 tensor b epsilon ID. So we're talking about two boxes. As such, so remember, I mean, n is equal to 2, so the indices are either epsilon 1 or epsilon 2. Yeah, we're speaking either about vector 1, 0 or 0, 1. It's part of the notation, but it's just this very simple thing. And so, let me just do a little example.
And what does it mean, row strict filling? It's like your okay.
Let me just do a little example.
Yeah, sorry.
I think these things are best explained by examples. So let's just so it has two rows because n is equal to 2. Let's say that's the shape, and now let's so I have a prepared little example where that would be the row strict filling. So it's not standard anymore because it's not column strict. Yeah, but I just keep everything here in descending order. And so the associated monomial will be, well, so for I have to look at the row of the entry to say whether I have an epsilon 1 or an epsilon 2. First guy is in the second row, so I have the epsilon 2 to start with. Then the 2 is also in the second row, so my second guy is also the epsilon 2. Then my 3 is in the first row, so I get the epsilon 1. Yeah, and I get some many epsilon 1s.
Yeah.
Epsilon 1, the epsilon 1, and another one, the epsilon 1. And then the 7th guy is again in the second row, so that would be the epsilon 2. And then another the epsilon 1. Yeah, so it's a very short notation for a long thingy. And so, well, but that's just how for in this example d equal to 8, the monomial standard monomial basis vectors in the tensor look like, right? And so, in other words, want to describe, want to compute these gamma tj. Yeah? So that for some standard Young tableau, we can say with which coefficient that particular monomial occurs. Let me just give that statement. So first of all, we only need to always record actually the second row, yeah, because everything else will be just the epsilon 1s, yeah. So we only need to know whether the epsilon 2s go and fill the rest with the epsilon 1s. x particular for n equal to 2. And this makes everything tractable. So we only need to look at the second rows. So we can actually write little truths here because everything will just depend on second rows. So here, I mean, it doesn't matter. You can write in 2 or not. And so then the theorem is that these coefficients, depending on the second row of T, would be aimed at, and J that we consider, that would be a sum over certain permutations. So that each summand is a product over all boxes in a permutation of J2. Yeah? So that the kth entry in here is equal to the kth entry of our x given T. Whenever this happens, so for all such k, there we will have a minus that very entry, minus 2k plus 1. So that's a very close formula. If I tell you which permutations I have to sum over here, it's a subset of all permutations of that second row that we're all the time looking at. So that all the entries are less or equal than in that given tableau for permutation in there. Yeah? So all permutations, that's kind of either compare less or equal to after computing J2 to T2 in each entry. I take all these permutations and then I'm summing over all these permutations. And note that, I mean, I'm enforcing that I don't get greater than. I might have some strictly less than, and then I don't get a factor here. So that when the product is over the empty set, because all my entries are strictly less, then this product would be just 1. Yeah? So it's usually for empty products. Yeah, so so this means that we have a closed formula. In other words, we don't need to look at the recursion. We just have straight ahead the coefficients for such a highest weight vector belonging to a certain part in the branching graph, also known as the fixed standard length tableau. So we can just compute the coefficients. Let me do it in one example to finish. So if we have in this example, so we need a tableau of the same size. Yeah? So if we were given T so now that better be standard. So 7. So if we want to, so that would be like a path in the branching going down to the 8th tensor power, down somewhere in the branching. We find that copy of L52, also known as L2 in the usual SL2 plates that are just given by one number. And there, in order to find out, so we know that there's some highest weight vector for this particular copy. And in order to find out, so it will be big sum. And we want to know how often this particular example here occurs. So what we need to look at is second rows and compare them. So the second row of J is equal to 1, 2, 7. So I can compute them either by the identity. So if it's just the identity, then I will have this satisfied that indeed somehow 1, 2, 7 is less or equal always than 257, yeah, which is this T2. So let me read off what I get for this particular permutation. Well, the product would be, so this is strictly less, I don't get a factor. This is also strictly less, I don't get a factor, but this is equal. Yeah? So for this K, I get a factor, and this is minus, so that entry is 7. Yeah, so I'm looking at that entry. Then I'm subtracting twice the position, which is 3. And then, one. Yeah? And that should be minus 2. Right? Okay. But I have yet another permutation, because I can also consider the permutation 217. Yeah, so I flipped the first two guys. All the other permutations would kind of conflict with these inequality conditions. Yeah, so these are the only two permutations I'm summing over. And what do I get here? So here I have equality, so I get minus 2 times. Minus 2 times 1, because it's the first position, plus 1. That would be the first factor. Well, that's the brackets for the signs. And then again, from the 7 minus 2 times 3 plus 1. So now that should be minus 1. And that is the minus 2 that we had before. So this is plus 2. Yeah. And now we sum over all our permutations, which are these two, to find that, alas, it's 0. And I want to make this particular example to tell you that there's quite a lot, I mean, there might be quite a lot of interesting cancellations actually going on. Right. Yeah. So it's not like, you know, like we're getting non-zero stuff all the time or so. But so in that case, so the gamma T2 J2 is 0, and we know that this monomial here does not appear in this VT.
Right.
Yeah, so it's, I mean, maybe it looks like bulky formulas, but it's really as easy as that to compute these things. And so if you want to have some maybe more satisfying example down here, then maybe let's just cheat a little bit, yeah, and say, okay, what if let's maybe instead of this monomial, let's look at a different one, yeah, when we get something non-zero. So let's take this one, where this is our new J2, because there this permutation doesn't work, yeah, because here we get a greater, so this would not contribute. This one actually gives the same result because we still only have equality at 7 years, so that was a very easy correction to make that like the green J2 is actually equal to minus 2. Right. And in that way, one gets these highest weight vectors, well, but here these combinatorics obviously really rely on just evaluating the second row. And so for bigger n, when we get more rows, there are more comparisons. There's more things happening because at the heart of this theorem, there's some consideration really saying that, well, as soon as, I mean, there's just one F, right? Mm-hmm. There's the observation that as soon as we apply that F, then it will send the epsilon1 to the epsilon2, but it cannot go back from there. And so it's like some quite nice situation, whereas for n equal to 3, we can never be certain whether such a guy is somehow taken up by another F3 moved by another F2 moved further down. Yeah. And if now somehow they come in the wrong order, then the whole result will be 0. And so there's like, this is much more difficult. Yeah. But n equal to 2 is still tractable. Yeah. Yeah, so that's what I want to conclude by. Thanks for your long attention.
Thank you. It was very nice. Okay, we're time for questions. I will all have to go, sorry.
Yeah.
We don't have him anymore here.
Right.
Yes, and Dalia too, and they said the talk was beautiful, and I also think that.
Thanks so much.
Thank you. It's really beautiful. That is the word.
Just the topic. It's I think it's one of the most beautiful like areas. Simply, it's like that. I mean,
Yeah, the combinatorics is stunning.
Yeah. So we're also currently thrilled somehow about how easy all of these observations are.
Yeah.
And so actually, like, there's one like kind of request to any one of you because so I mean this theory is like over 100 years old, depending on at which like new generation of input you look at. Maybe like the newer generations might be even already something like 40, 50 years old and so on. So as you already mentioned, I mean this is like related to so many things.
Right. Yeah, of course.
And also, so for example, there's computations of like these kind of decompositions in this abstract way, in this kind of crystal way that even tries to avoid to see anything about the vectors. But of course, there's like kind of I mean the crystals to be compared against somehow still. And then there's so one thing that Pablo and I are currently looking at would be like operators from the Yangian that will produce some things in the weight spaces further down below. But there it's like it's kind of the wrong corner. It's like SLN-1 sitting in the upper corner, the lower corner. Then there's anything under the name Clebsch-Gordon refers to physicists doing amazingly intimidating computations for kind of probably similar things.
Right.
But but we haven't been able to see that kind of structure anywhere so far. And we feel like it might be out there still. So if any one of you feels reminded, please. In this edit.
That's pretty cool. Very cool. Yeah.
Well,
Questions or remarks in that way, maybe?
No.
Okay.
no, I don't have any questions.
Then thanks again.
Okay, good.
Thank you.
Well, let's see.
Cool. Thank you. You want to take a coffee or something?
Yeah, sure, very much. And I would be curious. So I'm. It's been a long time since I think I know what to point at, but it's been too long.
Yeah, I mean, actually, it's for maybe.